Hello there and welcome to the normal distribution, one of the most common statistical distributions that there is, and in fact many different real life circumstances or distributions are in fact normal, where most things are average sort of height, weight and so on, but you have a few very high and a few very low values. Okay, so for example, male adult heights would have a normal distribution, babies' birth weights, and so on. Okay, now the typical shape of a normal distribution, which you might have seen before, is what's known as a bell curve. So it's this shape here. Okay, so in this case, X might be something like babies' weights, or let's say male. Let's say male heights. Okay, the taller ones going off to the right, so taller people off to the right, shorter off to the left. Okay, so it's always smaller on the left, and then in the middle here we have the mean, and you'll notice that the mean, okay, is always going to be in the center, because the mode is the value with the highest frequency. That is also the mode, and the median is also in the same place. So it's one of the important properties of the normal distribution is that the mean for a normal distribution, the mean and the median and the mode should be equal to each other. Okay, notice that the curve is symmetrical. You need to know these features. Notice that the curve is called a bell curve. Okay, and the other most important feature of a normal distribution is that we only use the normal distribution when we have continuous data. Now remember, continuous data is anything which is measured rather than counted. So anything along the lines of heights or weights, or IQ is a very typical example of the normal distribution, but anything where the data is continuous, so it's measured and the data has units. Okay, so for example, male heights would maybe be measured in centimeters. Okay, now what we need to realize in order to do any work with the normal distribution is that we say the area underneath the graph represents probability. Okay, and the area underneath the whole curve, then, because the maximum possible probability is always 1, the total area under a normal curve is also 1. And the way that we calculate probabilities using the normal can be shown in this diagram here. So we've got heights, perhaps male heights in centimeters, with the mean height. Remember, this is the mean, and the median and the mode is 180 centimeters. Taller people to the left, shorter to the right. If we wanted to work out the probability of a height, or someone having a height between 170 and 190 rather, which we write as P of X greater than 190, greater than 170, smaller than 190, we would represent that probability by this area here. So this blue area is the probability that X is between 170 and 190. Okay, and that's really the secret. Now, what is one of the most important factors also for a normal distribution? You cannot have the probability that X equals something. Unlike the binomial distribution that you've met so far, you can have the probability that X equals 1 or 2 or 3. Okay, that doesn't exist for the normal distribution. The probability that X equals 200, because we have continuous data, is essentially you are saying the width of a line, and a line has no width. So the probability that X is 200 doesn't exist, and we usually say that it's going to be equal to 0. Okay, remember. Okay, a little bit about the notation for the normal distribution. Remember, for the binomial distribution, where X has a binomial distribution, we used to write X, wiggle, and then B for binomial, and then the two parameters for the binomial were N and P. So you could have something like X has a binomial distribution where N is 30 and P is 0.2. Okay, for the normal distribution, we don't use N and P. The two parameters, okay, are this one here, which is mu, it's pronounced mu, and that is the mean, and this one here, which you've met before, which is the variance. And it's always the case that when we describe a normal distribution, we always put the mean first and then the variance second, not the standard deviation. Okay, so we would read this as X has a normal distribution, and it doesn't matter what sort of bracket you use, with mean, mu, and variance, sigma squared. Okay, and X is what we call a continuous random variable. Okay, so for example, if we had heights of male students are normally distributed with mean 172 and standard deviation 4, first of all we would define x. So x equals, let's just shorten it to male heights, and we would, using the notation, say x has a normal distribution with mean 172, so write that first. Notice if the standard deviation is 4, then the variance is going to be 4 squared, and quite often you'll see it written like that, okay, because that reminds you then that the standard deviation is 4 rather than using the variance. Okay, if we look at the second example here, masses of eggs from manor farm are normally distributed with mean 72. I could write in this case x has a normal distribution, mean 72, and then the variance is what we always put here, would be 3 squared. Right, there are some important percentages that you need to learn which are associated with the normal distribution. Okay, and the first of which is that 68% of the distribution should lie within 1 standard deviation of the mean. Now, as we know, the mean is here in the middle. So if this is the mean, that's mu. So so if I just draw a vertical line either side, so it's not very vertical, but you get the idea. Okay, so that this area here is 68%, okay, or as a decimal 0.68, okay, then here is the mean plus 1 standard deviation, and here the value here on this axis is going to be the mean minus 1 standard deviation. And if that's the case, either side, so 1 standard deviation either side of the mean should contain 68% of your population. Now if we go to 2 standard deviations either side of the mean, that proportion goes right up to 95%. So if I draw these 2 lines a bit further out still, this area is 95% or 0.95 if this is the mean, and then this is the mean plus 2 standard deviations, and this is the mean minus 2 standard deviations. So 95% of your population should be within between 2 standard deviations either side of the mean. Okay, if we go up to 3 standard deviations, and this is for a typical normal distribution, then 99.7%, now that's pretty close to the whole population, should be within 3 standard deviations of the mean. So I'm going to do a little mark here and a little mark here. So this is the mean. This is the mean plus 3 standard deviations. This is down here the mean minus 3 standard deviations. And notice that between those two is 6 standard deviations. Okay, and if that is the case, then this area here between here and here should be about 99.7%, or 0.997, which basically means that the range for a typical normal distribution, the range should be approximately 6 standard deviations. So if you know what the standard deviation is for a normal distribution, you should be able to work out the range. It's roughly 6 standard deviations. Okay, it's also fairly obvious then, if we're considering areas, that if we have a normal distribution, remember, which is symmetrical, then the mean in the middle, the area to the left of the mean should be 0.5, and the area to the right of the mean should also be 0.5. Okay, let's have a look at a first example of how we might use the normal distribution to work out probabilities. So we're told that we have some oak leaves, and the lengths of those leaves are normally distributed with a mean of 7.8 and a standard deviation of 1.2. Okay, so if I just draw that, okay, so in the middle is the mean, 7.8. Standard deviation is 1.2. Now, if I work out 3 standard deviations, so I do 3 times 1.2, well, that's going to be 3.6. That means that right at the top here, okay, so the most of the distribution of oak leaf lengths should be within 7.8 plus 3.6. So 11.4, okay, and right down here, so the smallest leaf that we would expect to find is going to be 7.8, take away the 3.6, which is going to be 4.2. So we would expect all of the oak leaves to be somewhere between 4.2 and 11.4 centimeters, and we normally label this axis here as x. I should have written actually x has a normal distribution with mean 7.8 okay, and variance 1.2 squared. Okay, so let's have a go at working out some probabilities using the information that we learnt on the last slide. So what is the probability that x is less than 7.8? Well, we know that it's a symmetrical distribution, so this area here is just going to be 0.5. Okay, and the probability that x is bigger than 7.8 is also going to be 0.5. That's the area to the right. Okay, so what's the probability that x is between 6.6 and 9? Now notice that if we do 7.8 plus the standard deviation 1.2, we're going to get 9, and if we do 7.8 minus 1.2, we get 6.6. So actually here we have, so if I'll just draw it again. Yeah. Okay, so we have the 7.8 in the middle, and notice that basically we've got one standard deviation either side of the mean, so 7.8, and that is 9. So that's plus one standard deviation, that's minus one standard deviation. So we know that this area here is going to be 68%. So the answer to that one is going to be 0.68. Right, if we want the probability that x is smaller than 9, if I just draw this again, okay, smaller than 9, okay, not very clear there. Okay, so there's my 7.8 in the middle, there's 9 over there. I know that from this diagram here, between 6.6 and 9 is 68%, so between 7.8 and 9 must be half of that, which is 0.34. We know that this area below the 7.8 is 0.5. Okay, so the probability that x is smaller than 9 is going to be 0.5 add 3.4, which is going to be 0.84. Okay, the percentage of leaves which you would expect to be less than 6.6 centimeters long, well, we already know there's the 7.8, and the 6.6, remember, was one standard deviation below, so this area here is 0.34. This area here is 0.5 to the right of 7.8. Less than 6.6 is going to be this area here. So it's what's left, which is just going to be 0.16. But they're asking for a percentage. So the answer there is going to be 16%.